Okay, so okay, so I have explained to you that lecture 12, 13, 14 we have covered longitudinal and shear strain. That will be strain, not stress. Local volumetric strain and local infinitesimal strain and similarities in properties of stress and strain tensor. And this was the definition of longitudinal strain at a point. So it is dependent on gradient of this displacement vector. So which will be a second order tensor. Then it is multiplied by the direction in which you want to find out the longitudinal strains. That will be vector again. Tensor multiplied by vector will be vector. And then it is dotted with that direction itself. So the whole thing will be scalar. Now I was giving one example. So suppose line segment. Suppose line element direction line element direction is along E1, right? Then you have to find the longitudinal strain. Then the longitudinal strain is given by, that will be given by epsilon x comma E1. So its value will be, let's put the values. So that will be half of, just have to put in this expression. So half of this grad u plus grad u transpose. So here you have grad u, so that is del u1 by del x1, del u1 by del x2, del u1 by del x3, del u2 by del x1, del u2 by del x2, and del u2 by del x3, del u3 by del x1, del u3 by del x2, and del u3 by del x3. You have this, and then plus transpose of this matrix. If you do that, so transpose will be del u1 by del x1, del u2 by del x1, and del u3 by del x1. Only second row will be del u1 by del x2, del u2 by del x2, and del u3 by del x2. And third row will be del u1 by del x3, del u2 by del x3, and del u3 by del x3. So this is transpose of gradient of u. So you have this. So half of gradient of u plus gradient u transpose, and then you have to multiply this with n vectors. N vector now is e1, which is, so e1 will be now, what will be e1? Can you tell me? So um, yeah, so e1 will be 1 0 0, because only first component will be present, other two are 0. And then you have dotted with e1 itself. So this is whole quantity, so that will be, so this whole quantity will be a vector. Yeah, so this whole quantity will be a vector, and then you have to dot this with this e1 only. So you have to do 1 0 0. So let's see what we get. So if you solve this, so there will be addition of, so this will be half of del u1 by del x1 plus half of del u1 by del x1. So this will be del u1 by del x1 only. Here on the second element will be half of del u1 by del x2 plus half of del u2 by del x1. Right. Similarly, you can find the whole tensor. Then you have to multiply it with the vector. So when you will multiply this with the vector, so what will you get? So you are going to get only the first column, because when you do multiplication, matrix and vector multiplication, so this will be multiplied, this element will be multiplied by 0 and this also will be multiplied by 0, so only you will be left with the first element. So you're only going to get first element of each and every column. So first element here, now we have del u1 by del x1. The resulting matrix will have first element as del u1 by del x1. Second element in first element will be del u1 by del x1. Then you will get this first column after multiplying by 100. You will get complete first column of the resulting matrix. So first column will be first element is del u1 by del x1. First column second element will be half of del u2 by del x1 plus del u1 by del x2, and then you have half of del u3 by del x1 plus del u1 by del x3. Now if you dot this with again 100, so what you will get? You will only get first element. So epsilon at point x comma e1. So you are getting as del u1 by del x1. And if you remember, this is a longitudinal strain in x direction, because e1 is the x direction. Okay, similarly you can find longitudinal strain in y direction also. So that will be del u2 by del x1. You can work it out and this will be the expression. Similarly, you can find longitudinal strain in third direction. So that will be del u3 by del x3. Okay. So obviously that is capital X. Now coming on to the shear strain. So you would have studied in the lectures that shear strain has, so what is shear strain? So shear strain is the change in angle between two initially perpendicular line elements. So let's say in the undeformed configuration you have, or in the reference configuration you have two line elements which are perpendicular to each other. Now after deformation, so in the deformed configuration there will be some angle, final angle between those line elements. So difference of the initial angle minus final angle. So that will be shear strain. So initial angle is 90 degree. So initial angle was 90 degree and final angle is, let's say, beta. So difference of that will be shear strain. So if I denote it with on the axis, so initially let's say these two line elements are perpendicular to each other. Now after deformation they have become like this. Finally they have this element in between them, which is, so this, finally they have this angle. So this angle is denoted by, let's say, beta. So your shear strain will be 90 minus beta, because this is the uh, change in angle of your line elements. Let me see. So the formula for this was alpha is equal to grad u plus grad u transpose, and it will be dependent on two directions. First direction will be direction of the first line element, and the second one will be direction of second line element, right? So because there are two line elements involved and we are observing the change in angle between these two line elements, So obviously there will be two directions. Now, so here I can write it. So I can write that it depends on the direction of the two line elements. Let me see. Okay. Now we can say that there is some significance of this term because this term was appearing in longitudinal. So this is a tensor, right? Gradient of u will be a tensor. So this gradient of u plus gradient of u transpose is appearing in this shear strain also and this longitudinal strain also. So there is a significance of this term. It is appearing here also. So there is a significance and it is known as strain tensor. So I can just write that significance of half of grad u plus grad u transpose. So this is known as infinitesimal strain tensor. Which is denoted by like this. So if we expand this half of grad u plus grad u transpose the coordinate system e1, e2, e3, obviously tensor has to be expanded with respect to some coordinate system. So if we do that, so what we will get? So we will get, if we can solve this, you can write above also we have written this grad u plus grad u transpose. If you add these two matrices, you will get del u1 by del x1, and here you will get half of del u1 by del x2 plus del u2 by del x1. And the third element will be half of del u1 by del x3 plus del u3 by del x1. Right. Similarly, first element will be half of del u1 by del x2 plus del u2 by del x1. Second element will be del u2 by del x2. And in the second row I'm talking about. So in second row, third element will be half of del u2 by x3 plus del u3 by del x2. Right. In the third row, you have first element, so that is del u1 by del x3 plus del u3 by del x1. Second element is half of del u2 by del x3 plus del u3 by del x2. And then the last element is del u3 by del x3. So this is the whole infinitesimal strain tensor that you have. Okay. There are some observations related to the strain tensor. So here the diagonal elements are representing the longitudinal strains and off diagonal elements are representing half of shear strain because shear strain will be double of this. Okay. So we can just write it here that diagonal elements here represent longitudinal strain along E1, E2, E3 direction, and you can say that off diagonal element represent half of shear stress. Then you have volumetric strain that you would have studied in your in the classes, the lectures. So volumetric strain is denoted by epsilon V. It is, so you would have seen the derivation. I'm just writing the formula. So it is determinant of deformation gradient tensor minus 1. So and deformation gradient tensor is given by identity tensor or identity matrix plus this displacement gradient tensor, that of u, right? So you can also write as, if you expand all this, so you'll get del u1 by del x1 plus del u2 by del x2 plus del u3 by del x3. So this will be your volumetric strain. So if you write here, so you can write it like this also. So it is trace of this infinitesimal strain tensor, because trace means summation of diagonal elements. If you sum all these diagonal elements, you will get this only, del u1 by del x1, del u2 by del x2, and plus del u3 by del x3. Now it can also be written as trace of this gradient of u. Okay, if you write this matrix gradient of u, so diagonal elements will be del u1 by del x1, del u2 by del x2, and del u3 by del x3, and you are taking trace means you will do summation of that, and then you can just substitute this infinitesimal strain tensor. So that is trace of infinitesimal strain tensor is given by half of grad u plus grad u transpose. Okay, these are the three formulas. Now you would also studied that we can just write deformation gradient tensor as identity tensor plus displacement gradient tensor, and then this can be written as, so I'm just writing this uh, this tensor, displacement gradient tensor, in terms of a symmetric and antisymmetric matrix. So symmetric matrix will be half of del u plus del u transpose, and antisymmetric matrix will be half of del u minus del u transpose, right? So you know that the second term is nothing but infinitesimal strain tensor. The third term you would have studied in the lectures. It is known as rotation tensor. Okay, so it is a local rotation tensor. So we can just write that local rotation tensor W. So expression for W is given by, so obviously we are expressing W in the coordinate system E1, E2, and E3. So expression for W is given by, so that is nothing but this half of grad of U minus grad of U transpose. So the diagonal terms will be 0 because grad U and grad U transpose have same diagonal terms. So it will be 0. So the non-diagonal terms will be half of del U1 by del x2 minus del U2 by del x1, and then it is an anti-symmetric tensor. So first or third term, so third term will be half of del U1 by del x3 minus del U3 by del x1. And then here you have minus of this term because it is antisymmetric, so here you have minus of this term. So here a minus of half of del u1 by del x2 minus del u2 by del x2. And then diagonal term will be 0, and this of diagonal term again will be half of del u2 by del x3 minus del u3 by del x1. And then again this term here will be, since it is antisymmetric, so it will be minus of this term. So this will be minus of half of del u1 by del x2 minus, and then the next term will be half minus of this term, so we can just write it as minus half of del, sorry, actually, yeah, so it is 3 2, so that will be minus of 2 3, so it will be minus of this term here. So you can write half of del u2 by del x3 minus, this will be 2 not 1. Okay, so and obviously the diagonal term will be 0. So this is the overall, so this is the overall rotation tensor that you have. So, and also you would have studied in the previous lecture that we can express any antisymmetric tensor in terms of a vector, and that vector is known as axial vector of that tensor. So we can write this antisymmetric tensor W in terms of axial vector. So component of axial vector W is, so that is given by W underscore, that is vector, so that's why I'm using underscore sign, only one underscore in the coordinate system e1 e2 e3. So that is given by, so there are three independent components in antisymmetric tensor, so this is given by those three independent components. So first component is half of del u3 by del x2 minus del u2 by del x3. Second is del u1 by del x3 minus del u3 by del x1. I'm just writing in the next line. And the third component is half of del u2 by del x1 minus del u1 by del x2. So this is the axial vector corresponding to this antisymmetric tensor W. Then you would have studied related to similarity in the properties of stress and strain tensor. So let me recapitulate that. So just write okay. So what similarities do you have? So here I'm writing stress, and here I'm writing strain. Right? Let me draw a line in between. In stress you have normal stress, so that is given by sigma, which is a stress tensor, and which is plane normal on the plane on which you want to find out this normal stress, normal component of stress. So that is given by sigma n dot n. So it is actually normal component of traction. And then you have here you have normal strain, longitudinal strain. So that is given by this infinitesimal strain tensor and length. Here n was the plane normal on the plane on which you want to find out this normal component of the traction. But here this n is along the line segment. So n is the direction along which you want to find out the longitudinal strain. So then you have shear stress tau mn. So that was given by sigma n dot m. Okay. So again, this was the plane normal, and this was the direction in which you wanted to find out your shear stress. Okay. And now you have gamma mn, that is shear strain. So that is given by twice of epsilon n dot m. Here n and m are the directions of two line segments that you consider for finding this shear strain. So let me just define. So n is plane normal, m is direction along which we measure shear. And then here also we have n as direction of line element. Here the meaning is different. So n is direction of line element. And m is direction of line element perpendicular to n. Okay. So that is basic difference. And then we also concluded that, I mean, in the lecture, sir also concluded that strain tensor is symmetric. This is also symmetric. You can see from the expression of the strain tensor. Okay. Then we have Mohr circle for strain tensor also. Mohr circle for strain. So to draw it, so center will be given by epsilon xx plus epsilon yy divided by 2 comma 0. So this is the center of the Mohr circle that you get. Epsilon xx and epsilon yy are the longitudinal strains in x and y direction respectively. And the maximum shear strain that is given by double of the radius, because this axis is half of shear strain and this axis is the normal strain, right? This is half because in this formula, if you compare this, here double is coming, right? So that's why on this axis half of shear strain will come. Because in the Mohr circle of stress you plotted this quantity, it does not contain any double sign. So here also you should plot only this quantity. This quantity is half of the shear strain. That's why we are plotting this half of shear strain only. So obviously half of shear strain will be equal to radius. That's why the maximum half of maximum shear strain will be radius. So that's why maximum shear strain will be double of radius. So now let's say you have now you want to write principal strain component. Okay. So that is given by center plus minus radius, right? So center is epsilon xx plus epsilon yy by 2, and then you have plus minus radius. So this will be the value of principal strain components. Similarly, you can decompose your strain tensor into a volumetric part, volumetric strain tensor, and deviatoric strain tensor. Volumetric strain tensor is responsible for changing the volume of your element, and deviatoric strain tensor will be responsible for changing the shape of the element, right? So decomposition of strain tensor, that is given by 1 by 3 of J1, so it is first invariant of strain tensor. So this is volumetric strain tensor. And then from the total strain tensor, if you subtract this volumetric strain tensor, so you get the deviatoric strain tensor. So this part is known as deviatoric strain tensor. Right. So now, obviously this J1 is first invariant of strain tensor. First invariant is nothing but summation of the diagonal elements. So it is also known as, which is also known as volumetric strain. So J1 is nothing but equal to volumetric strain. So now we have strain compatibility conditions. There are 6 strain compatibility conditions that you would have studied. Strain compatibility. So any strain matrix cannot represent strain tensor. So the strain matrix must satisfy certain conditions, certain compatibility conditions in order to be that matrix to be strain tensor. So your strain matrix must satisfy these compatibility conditions so that it becomes strain tensor. And these conditions are, so let's say you have strain matrix. Now it is a matrix only. So the components are epsilon xx, epsilon xy, epsilon xz. I should write gamma, not epsilon. Um, so this is half of gamma, I think. Okay, anyway, if I write gamma, so that will be half of gamma, but I'm just writing the tensorial strain. So tensorial strain will be epsilon xy, tensorial component of the shear strain, and this is xz. So yx, yy, yz, xz, xy. Sorry. So this will be zx, zy, zz. So this matrix, strain matrix, cannot become strain tensor. For this matrix to be strain tensor, it must satisfy certain compatibility conditions, and those conditions will be given by. So those are, I'm just writing those conditions. So first condition is del, del square epsilon xx divided by del y square plus del square epsilon yy divided by del x square. Obviously, these are all capital quantities. I should not write small. Let me correct myself. Because capital letters represent reference configuration or undeformed configuration here. This is epsilon xx, epsilon xy, epsilon xz, yx, yy, yz, zx, zy. Similarly, first compatibility condition is del square epsilon xx divided by del y square plus del square epsilon yy divided by del x square, and that should be equal to del square gamma xy divided by del x del y. So this condition should be satisfied. If you have this matrix, so this condition should be satisfied. So this is only first condition. Similarly, there are 6 conditions. So del square epsilon yy divided by del z square plus del square epsilon zz divided by del y square, that should be equal to del square gamma yz. Actually, I should use capital letters. Yz, so over del y del z, right? Here also this is capital. So this is the second compatibility condition. Similarly, the third one is del square epsilon xx over del z square plus del square epsilon zz over del x square. So that should be equal to del square gamma xz over del x del z. So these are the first 3 compatibility conditions, and last 3 are del by del z. Then you have differentiation of shear strains, del gamma yz over del x, del gamma zx over del y, del gamma xy over del z. So that should be equal to twice of del square epsilon zz over del x del y. Then you have del by del x, del gamma xy over del z. Okay, I'm just writing these conditions, so please bear with me. So del by del y, so that will be equal to del of gamma xy over del z, del of gamma yz over del x. You can just check whether I may do some mistake also in writing these conditions. You can just verify. But I'm trying to write as correct as possible. Okay, so these are strain compatibility conditions. So your strain matrix must satisfy these strain compatibility condition in order for the strain matrix to be strain tensor. So now we have some plane stress conditions also. So for plane stress conditions, plane strains. For plane strain conditions, we have epsilon xx. So everything will be a function of x and y. Nothing will be a function of z. So epsilon xx will be a function of epsilon. So that will be a function of only x and y. It will not vary with z. So epsilon yy. So that will be a function of x and y only. And gamma xy, that will also be a function of x and y. And all other strains will be zero. So only in plane strains will be there, and out of plane strains will be zero. Your plane is xy plane obviously here. So epsilon zz and gamma xz and gamma yz, these three will be zero. So for plane strain conditions, first, so out of all these compatibility conditions, 5 compatibility conditions are already satisfied for plane strain condition. So we only need to satisfy only one extra compatibility condition, and that condition is, let me just write. So we need to satisfy only one strain compatibility condition for plane strain problem. And that condition is given by this one, del square epsilon xx over del y square plus del square epsilon yy over del x square. That should be equal to del square gamma xy over del xl. So this is nothing but the first compatibility condition, right? And rest all you can check actually. Rest all these 5 other compatibility conditions will be satisfied by itself. Just put these quantities here. Remember that it is only a function of x and y, and all these terms are zero. If you put this, all the other 5 compatibility conditions will be automatically satisfied. So let's start with problems. So problem 1. So problem says the position of a particle initially at x1, x2, x3 is defined by so x1 is equal to x1 plus k into x3, and x2 will be equal to x2 plus k into x2, and obviously x3 is equal to x3. So from here you can define u. So u1, so that is nothing but x1 minus x1, because this is displacement, so this will be final position minus initial position, so that is given by k of x3. Similarly, your u2, that will be x2 minus capital of x2, that will be capital of k times capital of x2, and your u3 will be 0 because x3 minus x3 will be 0. So, and obviously k is given to you, so value of k is 10 to the power minus 5. Okay. So what you have to find is part A. You have to find the components of strain tensor. Firstly, you need to find components of strain tensor, and then you need to find the unit elongation of an element initially in the direction of E1 plus E2. So can you try to do this question? So position of particle as a function of reference configuration is given to you, and then you have to find out the component of strain tensors. I have written the displacement vector. Once you have displacement vector, then you can calculate displacement gradient, and once you have displacement gradient, you can find the strain tensor because it is half of displacement gradient plus displacement gradient transpose. So please find strain tensor. Once you have strain tensor, you can just find unit elongation of element in the direction E1 plus E2. So E1 plus E2 will be your n vector, and unit elongation will be longitudinal strain. So that will be given by strain tensor times n dot with n. Once you have strain tensor, you can just multiply it with this vector E1 plus E2, and then dot with this vector itself. So you will get longitudinal strain or unit elongation in this direction. Okay. Please do that. Okay, so let me just. It's a straightforward question, but maybe difficult for some of students who are watching this first time or who are doing such type of questions first time. So let me do the solution. So the solution will be, so your strain tensor is given by half of grad of u plus grad of u transpose, right? So grad of u, you know that how to determine the second order tensor now. So because gradient of a vector is a second order tensor. So we have already written the expression for epsilon. So firstly, let's calculate grad of u. So grad of u, so grad of first element is del u1 by del x1. So del u1 by del x1, again this is not function of x1, so this will be 0. So del u1 by del x2, that will also be 0 because u1 is only a function of x3. So del u1 by del x3, so that is k. Similarly, del u2 by del x1, so that will be 0. Del u2 by del x2, that is k, and del u2 by del x3, that is 0. And third u3 is 0 itself, so this differential will be 0. This is your displacement gradient tensor. Now you can easily calculate your strain tensor, infinitesimal strain tensor. So that is given by half of grad u plus grad u transpose divided by 2. So that will be, do that. So 0 plus 0 will be 0, and here this will also be 0, and here you will get k plus 0 divided by 2. So that will be k by 2, and here you will get 0 again, and here you will get k plus k by 2. So that is k. Here you will get 0 again, and here at this position because when you will do transpose of this, so the first row will be 0 0 k, so this element will be 0 plus k by 2, so that will be k by 2. This will be 0, this will be 0. These are the components of strain tensor. So component of strain tensor you have found out. Now the second part, you have to find the elongation of element in the direction this. Firstly, you need to find out the unit vector along this direction, so that will be E1 plus E2 divided by its magnitude, which is root 2. This is a unit vector now, right? Now since you need to find out the longitudinal strain, so that is given by epsilon. So that is nothing but this strain tensor times this direction and noted with this direction itself, right? Because it was strain tensor times n dot n. So now your n vector, which is this e cap. So if you do that, so you just multiply. Now you have matrix 0 0 k by 2. So this is your strain tensor, and you multiply with this vector. So this is nothing but, so 1 by root 2 I'm writing here, and this is 110, and then you dot this thing again with this 1 by root 2 and 110, right? So firstly, if you multiply, so you'll get 1 by root 2 outside and 110. So first element will be 0, second element will be k, and third will be k by 2, right? And then if you dot with this vector, right? So finally, what will you get? So firstly, the first element will be 0 plus, so 1 by root 2, 1 by root 2 will be 1 by 2, obviously. Now this will be 1 by 2, and then first element will be 0, second element will be k. So finally, you will get k by 2. Third will be 0. So you get k by 2, which is 10 to the power minus 5 by 2. So this is the amount of elongation that you will get. So you see how much small is it, right? So it's very small. It is of the order of 10 to the power minus 5. So it's very smaller. It's very smaller than 1. So let's go to problem 2. You can ask me if you have any doubt in this question. So this was the question. If you have any doubt, you can ask me. Let me just share my screen again. Yeah, so let me go to the next one. Next question. So next question is problem 2. So you have to consider the following displacements. So these are given by u1 is k times price of x1 square plus x1 x2, and u2 is given by k times x2 square, and u3 is 0, and k is 10 to the minus 4. To find the unit elongations and the change of angles for two material elements. So to find it for two material elements, first material element is given by this quantity d capital X1, that is dx1 E1. So it's in the direction of E1, and the second is in the direction of E2. So these material elements emanate from a particle which is designated by capital X is equal to E1 plus E2. Okay. So let's do this. So you have following displacements given to you. To find unit elongation and the change of angles for two material elements. First element is in direction E1 and second is in direction E2, and that is emanating from particle whose position vector is given by E1 plus E2. Right. So firstly, let's find. So to find elongation and change of angle means you need to find longitudinal strain and shear strain. So to find that, so you need to find, let's say, gradient of displacement vector. So displacement gradient vector, because it will be used in both finding longitudinal strain and shear strain. So that is given by, so components will be given by, first component is del u1 by del x1. So if you differentiate del u1 by del x1, so that is given by 2k x1, right, plus, I'm sorry, I think this will be 4, yeah, plus k times x2. So this will be your first component. Now you have second component is del u1 by del x2. So if you do that, so you get k times x1. And third element will be del u1 by del x3, so that will be 0. Second row will be del u2 by del x1, so that is 0. Del u2 by del x2, so this is 2k x2, and del u3 by del x3, so that is 0. Similarly, del u3 by all the components will be 0 because u3 is 0. So now you have this displacement gradient tensor. Now you can easily find the infinitesimal strain tensor. So that is given by half of grad u plus grad u transpose. So if you write in terms of metrics, so you'll get, so first element will remain as it is, so 4k x1 plus k x2. And second one will be k x1 by 2. This will be 0. And since it will be symmetric, so this one will be also be given k x1 by 2. And this will be 2k x2 because diagonal elements will remain same. And this will be 0. So 0, 0. So it's a kind of plane strain case because this third row is completely 0. So it's a plane strain condition. And obviously this, if you remember, this is nothing but gamma by 2. So it is shear strain divided by 2, this component, because shear strain is double of this component. So because obviously shear strain is, in shear strain you do not have this half. Okay, so that's why, but this component will contain this half. That's why shear strain, this is half of shear strain. The shear strain will be double of this component, and this is nothing but diagonal terms is longitudinal strain. So now your position vector of the particle, so your particle position vector, so that is given by 110, right? So if you put this, and now you can try to find out unit elongation for dx1. So let's try to find out unit. So there are two material elements. So first let's try to find out for material element 1. So in unit elongation for this dx1. So that's dx1 is given by, so it's d, so its length is dx1 and its direction is e1. So unit elongation, for unit elongation we'll have to take this vector e1. So that is given by epsilon 1 1. So that is nothing but this first component, first row, first column. So that is 4k x1 plus k x2, and x1 is 1 here and x2 is also 1. So as I told you that the strain tensor, so this longitudinal strain tensor, it depends on two things. First one is the material point, coordinate of the material point that we are putting now, and second one is the direction. So direction we have already accounted for by, because this strain tensor has been expressed in E1, E2, E3 coordinate system. So its first element denotes along E1 direction, right? This is along E1 direction, longitudinal strain along E1 direction. This is longitudinal strain along E2 direction. And this is longitudinal strain along E3 direction. So yeah. So now let's put the coordinates of this point. So you'll get 4k plus k, so that you will get 5k. Right? So you will get 10 is power minus 5 into 10 is power minus 4. And then epsilon 2 2 also you can find out. So this will be second diagonal element. So that is 2k x2. x2 is 1, so you get 2k. So 2 into 10 is power minus 4. Right? Now change in angle between two line elements. You have to find out. So change in angle so between two line elements. So that is nothing but shear strain that is given by, so that is gamma, and gamma is nothing but double of this shear strain that you have, double of this, double of 2k x1 by 2, so double of k x1 by 2, so that will be k x1. So that you have to find out at x1 equal to 1 and x2 is equal to 1, because here you have x1, here you have x1 equal to 1 and x2 equal to 1. So if you do that, so you get k, so that is 10 to the minus 4. So this will be in radian. So now you have find out. So this is longitudinal strain along this dx1, and this is longitudinal strain along the second material element, and this is change of angle between those two material elements. That's how we have solved this question. Let's go to the next question. So you have problem 3. So problem 3 will be given by, so you have to find for the displacement field, is this one, u1 is k times x1 square. So I know it's all going mathematical, but there is a very physical significance behind it. So when I say u1 is k times x1 square, so let's say you have this somebody in reference configuration, right? And let's say there is a line element here in x1 direction. So, and this is, let's say, after this is some deformed configuration. Line element will be something like this. I don't know, but maybe let's say this, it is facing this elongation in x direction as of now. So what kind of elongation it will face? It will face quadratic elongation, because here quadratic displacement. So displacement is quadratically dependent on x1. So let's say at this point your displacement will be kx1 square. So this point will get displaced by kx1 square. Now the next point, as you are increasing in x, your displacement will also increase quadratically. So displacement of this point will be more than the previous point, and there is quadratic dependence. So there is a meaning behind it, because it is telling about how your line elements are going to deform from the reference configuration to the current configuration. So, but we are following mathematics because we cannot always visualize. So that's why we develop generalized mathematical formulations, and we rely on those formulations, because those formulations will give exact results, and we need not to visualize anything. We can visualize results, but the analysis part, we can visualize the results and do the analysis, but the calculation part we need not to do or put our intuition in the calculation part as well. Once the general mathematical framework is ready, you just have to follow that framework. Obviously, in the derivation of that framework, you will have to put some intuition and physics. So, x2 x3 and u3 will be k times 2x1 x3 plus x1 square, and k is given to you, which is 10 to the minus 6. Right? So you have to find what you have to do is you have to find the maximum unit elongation for an element that is initially at 100. So initial point is given to you, and you have been asked to find out the maximum unit elongation for an element that is initially at 100. Maximum unit elongation means you need to find out the maximum value of the principal component of the strain. So this principal component of the strain denotes the longitudinal components, and the maximum principal components denotes the maximum value of the longitudinal components, and maximum among those principal values will denote the maximum unit elongation for this element. So let me just, everything starts with, so in order to find out the principal values of the strain tensor, you need to find out strain tensor itself first. Then you have to do eigenvalue analysis, and then eigenvalues of that strain tensor will give you the principal values, and maximum among those principal values will give you maximum unit elongation. So let me find out strain tensor first. So that is dependent on displacement gradient tensor. So displacement gradient that will be given by gradient of u. So that will be del u1 by del x1. So this is 2kx1. Del u1 by del x2 0 0. Del u1 by del x3 will also be 0. Right, and okay. Similarly, this is del u2 by del x1, that is 0. Del u2 by del x2, so that is kx3, and del u2 by del x3, so that is kx2. And then you have del u3 by del x1, that is 2kx1, del u2 by del x2, oh, sorry, I think so del u3 by del x1, so that will be uh, 2kx3 plus 2kx1, and del u3 by del x2, that will be 0, and del u3 by del x3, so that will be 2kx1. This is what you will get. Now if you put the values of x1, x2, x3, so x1 is 1, x2 is 0, x3 is 0, so we'll just put the values, so we'll get 2k here, 0, 0, and x2, x3 are 0, so this will be 0, and here also we'll get 2k, and here also we'll get 2k. I think I have committed a mistake here, so that's it. Del u3 by del x1, so that is not 0 actually, so that is um, this will be symmetric, so here also you will get just wait. Yeah, that is fine, I think. This will not be symmetric. The strain tensor will be symmetric. Anyway, so okay. So you will get 2k 0 0 0 0 0 2k 0 2k. Now if you find out strain tensor, so that is nothing but half of grad u plus grad u transpose. To do that, so diagonal elements will be as it is. This will be 2k, and so there is no. So this will be 0, and if we will transform, if we'll do transpose of this, so here this will be 2k 0 2k. So 0 plus 2k by k will be k here, right? And similarly here you will have 0 because it is symmetric, so this element and this element will remain same, and this element is 0, so diagonal elements will obviously remain same, and of diagonal elements will really change. So this will again be 0, this is symmetric, so this will also be k. So this is the strain tensor that you will get. You can just directly put the values also. You just you have gradient of u, then you find transpose of gradient of u, and then you add it, you get this matrix. Now you need to do eigenvalue analysis. So what you need to do is you have to do this e minus lambda times I. So determinant of that you have to put equal to 0. So if you do that, so you get 2k minus lambda 0 k 0 0 minus lambda and 0 and k 0, and determinant of this will be 0. So if you solve this, so firstly, what will you get? So you'll get 2k minus lambda, and then you have minus lambda times 2k minus lambda. So that is the first term, and then you'll get plus of k times 0 minus 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 will be plus lambda times k, right? So this will be 0. So you take lambda to be common. So if you take minus lambda to be common, so you'll get 2k minus lambda to the whole square and minus of k square equal to 0. Okay. So if you solve this, so either lambda is equal to 0 or 2k minus lambda is equal to plus k, or 2k minus lambda is equal to minus k. Okay, so from here, what will you get? You will get lambda is equal to k, and from here, you will get lambda is equal to 3k. The maximum value is lambda is equal to 3k. So you can just say that lambda 1 is equal to 3k. This is maximum value. Lambda 2 is equal to k, and third principal component will be 0. So you can just say that this is the maximum value of the principal strain tensor. I mean the maximum value of the maximum principal value of the strain tensor. So that's why this will be the maximum unit elongation. You can say that maximum unit elongation at 100, that is 3k. So this is the maximum. So this is the magnitude. So at a particular material point, you have in a particular direction you have this maximum unit elongation, and you can find that direction also because that direction will be eigenvector corresponding to this eigenvalue, and the magnitude is given by this eigenvalue itself. So if you find the eigenvector, you will get the direction also. This is your homework. You can just find the eigenvector. So you will get at a particular material point in a particular direction, you have this principal maximum principal value, which is maximum unit elongation. So let's go to problem number 4. So it's given by the matrix of an infinitesimal strain tensor which is given as this. So this is k1 x2 and 0 0 and 0 minus k2 x2 0. So this is given to you that this is matrix of an infinitesimal strain tensor. So what you need to find out is you have to find the location of the particle that does not undergo any volume change. Okay, and part B you have to find what should be the relation between K1 and K2 so that no element changes its volume. Okay, so you have to find first the location of the particle that does not undergo any volume change. Second, you have to find the relation between K1 and K2 so that no element changes its volume. So you know that the volumetric strain is given by trace of the strain tensor, so that is nothing but summation of diagonal elements. So that is K1 x2 minus 2 K2 x2, right? That should be equal to 0 because there should not be any volumetric change. The volumetric strain should be 0. So if you took K1 minus 2 K2 and x2, that is 0. So for the first part, you have to find the location of the particle that does not undergo any volume change. So let's say if K1 is not equal to 2K2, so x2 will be 0. So location will be x2 will be 0. At x2 equal to 0, the particle at all the locations where x2 is 0, particle will not undergo any volumetric change provided this K1 is not equal to 2K2. Okay, but so this is part A. But if this K1 but if this K1 is equal to 2K2, then this relation will be satisfied irrespective of the value of x2. Right? That means all the elements will get 0 volumetric change. So the answer for the second part is what should be the relation between K1 and K2 so that no element changes its volume. So it means K1 should be equal to 2K2. then irrespective of the value of x2, all the elements will undergo zero volume change. So let's go to problem number 5. So you have displacement gradient matrix at a point in a body is given by H. So that is del u by del x, del u by del y is 0, del u by del x, sorry, this is del v, not v. So this is del v by del x, this is u, del v by, this is v, and this is y, this is y. Okay. Del u by del y equals 0, and this is 0, 0, 0. This is, you have displacement gradient matrix. So you have to write the conditions for zero infinitesimal rotation. So solution for this is, firstly you need to write out rotation tensor. So your rotation tensor should be equal to 0 tensor. Okay. So rotation tensor is, and obviously your gradient displacement gradient tensor is given to you, so that is H tensor. So rotation tensor, we have written the expression above also, so you can just directly write that expression. So this is 0, this is 1 by 2 del u1 by del x2 minus del u2 by del x1, and 1 by 2 del u1 by del x3 minus del u3 by del x1, and then this is 0, and this is 1 by 2 del u2 by del x3 minus del u3 by del x2, right? And this is 0, and rest of the part obviously here is antisymmetric. You can write other elements because it is antisymmetric. Okay, so now, so this each of the elements should be 0 because we want the condition for 0 infinitesimal rotation. So if you see del u1 by del x2 and del u2 by del x1, so this we cannot interpret from here, but this del u1 by del x3, which is this element, it is already 0, and del u3 by del x1, which is this element, so it is 0. So this term is already 0, right? Similarly, del u2 by del x3, which is this element here, which is 0, and del u3 by del x2, which is this element here, this is already 0. So this also will be 0. This term will also be 0. So only non-zero term left is this del u1 by del x2. So this del u1 by del x2 should be equal to del u2 by del x1. So if you compare from here, so del u1 by del x2 is nothing but del u by del x. So del u by del x. Del u2 by del x1 is del v by del. Sorry. So del u by del y. So this should be equal to del v by del x. From this. So these off diagonal terms should be equal, only then a rotation tensor will be 0. Okay. And only then there will be 0 infinitesimal rotation. These off diagonal terms should be 0. Del u by del y should be equal to del v by del x. Okay, coming on to the next problem. So it is problem number 6. So it says we have given the following formula for strain components. And that is given by epsilon xx. This is equal to 5 plus x square plus y square plus x4 plus y4. And this is epsilon yy, which is 6 plus 3x square plus 3y square plus x4 plus y4. And then you have gamma xy. This will be capital XY, just so gamma xy, so which is 10 plus 4xy times x square plus y square plus, and then you have epsilon zz and gamma yz and gamma zx equals 0. So what you have to do is you have to determine whether the above strain field is possible or not. And if it is possible, you have to determine displacement components in terms of x and y. And you have to assume ux is equal to uy equal to 0 and wxy equal to 0 at the origin. So at x is equal to 0, y is equal to 0, z is equal to 0, you have to assume these three conditions. The second part says for the state of strain given in previous problem, you have to write down the volumetric and deviatory parts, and you have to also determine the volumetric strain. So this is the question. So the strain field is given to you, and you have to determine whether the above strain field is possible or not. So you're able to see that this is a plane strain condition. So only 5 compatibility conditions will already be satisfied. So you need to satisfy only one extra compatibility condition. So once you check that condition, and if it is satisfied, then strain field will be possible. And if it is possible, you have to determine the displacement component in terms of x and y. So you have to integrate this strain field, and you have to put all these three conditions to find ux, uy. Okay. I mean those displacement components. And once you have the displacement components, you have to write down the volumetric and divisory part of the strain. And you have to determine volumetric strain also. Okay, so let me just start the solution. So we can just say that above strain field is plane strain condition. So the above strain field represents a plane strain condition. So only 1 out of 6 strain compatibility condition need to be checked. Other 5 are already satisfied, or we can say that trivially satisfied. So the condition that you need to check is del square epsilon xx over del y square, del square epsilon yy over del x square. So that should be equal to del square gamma xy over del x del y. So if you differentiate this del square epsilon xx over del y square, so to differentiate once, you will get 2y plus 4y cube, and if you differentiate twice, you will get 2 plus 12y square. So first term will be 2 plus 12y square. The second term, if you differentiate this epsilon yy with respect to x twice, so first term, if you differentiate once, you'll get 6x plus 4x cube, and if you differentiate twice, you'll get 6 plus 12x square. So here also you get 6 plus 12x square, and then you have to differentiate gamma xy with respect to x and y. So well, if you differentiate with respect to x, you will get 4y, and then here you will get 2x plus 2, and if you differentiate with respect to y, you will get 4 times, so 2 will not be there, so you will get 4 times. So if you differentiate once with respect to, let's say, x, so you get 4y times 2x, right? And if you differentiate with respect to y now, so you get 8x. So I'm doing some mistake. Oh yeah, you have to apply product rule also. Anyway, so let me differentiate it explicitly. So let me first, I'm just not writing this term here. So this term. So let me first do del gamma xy over del x. So if you do that, so let me first write the expression for gamma. If you do that, you will get 10 plus 4x cube y plus 4xy cube plus 8xy, right? Now if you differentiate del xy by del x, del gamma xy by del x, so you will get 12x square y plus 12xy square plus 8y, and then you will get del square gamma xy over del x del y, so you will get 12x square plus 24xy plus 8. Oh, sorry, so you 12y square plus 8. Okay, so here this way now some mistake. So here you will have 4y cube. You will differentiate again. So del y del x. Now you're differentiating with respect to y, so you'll have 12x square plus 12y square plus 8. This is fine. Now if you put it here, so it will go here at this place. So this will be 12x square plus 12y square. Plus 8. This is equal to left hand side, because if you see this is 12y square plus 12x square plus 8. So hence these given strain satisfies strain compatibility conditions, so these strains are possible. If it is possible, you have to determine the displacement component in terms of x and y. So to find out displacement component in terms of x and y, so what will you do? So epsilon xx, which is given by del ux by del x. So if you find out ux, so that will be integral of epsilon xx respect to dx plus some function of y, right? Because if you differentiate this, now you will get del ux by del x, that will be equal to epsilon xx. And since this is a function of y, so differentiation of this will be 0. So just integrate epsilon xx with respect to x. So obviously this is here the constant of integration. You would have studied in BTech first year mathematics course how to integrate partial differentials. So ux will be, so if you integrate epsilon xx, so what you will get? This will be 5x plus x cubed by 3 plus y square x plus x5 by 5 plus y 4x. So I'm just writing here, so 5x plus y square x plus x5 by 5 plus y 4x plus f of y will be there. Okay. Similarly, if you find y, so that is nothing but del uy by del y. So try to find out uy, so that will be integral of epsilon y with respect to dy plus some function of u of x. Now if you differentiate del uy by del y, so this will go to 0, and here we get epsilon y. So del uy by del y will be epsilon y again. So this equation satisfies uh, this equation. So now if you put uy, if you integrate epsilon y with respect to y, so epsilon y is given to you here. If you integrate this, so you get 6y, 3x square y plus 3y, so y cube, 3y, 3 by 3, so 3y cube by 3, so this will be y cube plus x4y plus y5 by 5. So writing here, so we'll get 6y plus 3x square y plus y cube plus x4y plus y5 by 5 plus g of x. Right? Now you need to find gamma xy. So gamma xy is nothing but del ux by del y plus del uy by del x. So if you find out, so you can use this expression only to find out. So del ux by del y, if you do that, so what will you get? So this term will go to 0, this will also go to 0, so here you will get 2yx, this will also go to 0, here you will get 4y cube x plus f prime y. So you will get 2 2xy plus 4xy cube plus f prime y. Now if you differentiate this del uy by del x, so this term will go to 0, here you will get 6xy, this term will go to 0, here you will get 4x cube y, this term will go to 0, here you will get g prime x. Finally what you will get is 6xy plus 4x cube y plus g prime x. Now compare this with the term gamma xy given in your question. So gamma xy is 10 plus this one, so I had expanded this. So if you, so gamma xy, so this gamma xy we have calculated from the displacement field that we have obtained by integrating del ux by del x and del u by del y, del uy by del y. Actually here in this displacement field, this fy and g of x are unknown, so we need to find out this f of y and g of x. So that's why I'm doing all these calculations. So because if you know fy, f of y and g of x, then you will have the whole expression for u of x, ux and uy. So now, so gamma xy can be found out using this displacement field, and gamma xy will be given to you also. So gamma xy given gamma xy is um, so this is 10 plus 4xy x square plus y square plus 2. Now if you compare with this, so let me just expand. So 10 plus 4x cube y plus 4x y cube plus 8xy, right? So if you compare the terms above here, so with this and this, 4x cube y is similar to 4x cube y, and 4xy cube is similar to 4xy cube. So these two, so this term here is similar to this term, and this term here is similar to this term. Now you have f prime y, okay, and here you have 6xy plus 2xy, that is 8xy. So you are left with 10 only. So this 10 should be equal to f prime y plus g prime x. So finally you have f prime y plus g prime x. So that should be equal to 10. So, but you cannot solve because only you have this one condition. You cannot solve for f prime y and g prime x. But what you can say is you have f prime y. So that is equal to 10 minus g prime x. So since this is a function of x and this is a function, this is a constant, so this whole term is not a function of y. So I'm just taking this whole term to be, let's say, c1. Okay. So if you integrate now, so f prime y is c1, which is again a constant because it is not dependent on y, so that's why it's constant when you integrate with respect to y. So if you integrate this, you will get f prime y is equal to c1y plus c2, right? So this is one equation, and then you have here from this one only g prime x, g prime x is equal to 10 minus c1, right? And this c1, uh, Okay. Okay, so g prime x is integral of, let me just see. Okay, so let's say this c1 g prime x is nothing but 10 minus f prime y. So we can say that g prime, so g of x is, g of x will be equal to 10 minus f prime y times x plus c2. And this 10 minus f prime y, so if you see from here, f prime y is nothing but c1, so we can substitute here. So g of x is uh, c1x plus c2. Anyway, so let's keep this as it is. Now you have three more conditions given to you. The first condition is u of x is 0 and u of y is 0 and w of xy also equal to 0. These three conditions at origin. So at x equal to 0, y is equal to 0 and z is equal to 0, and z is obviously not there. So at x equal to 0, y is equal to 0, your ux 0, uy is 0 and wxy are 0. So if you put in this equations, so using the displacement boundary condition, because that those are displacement boundary condition at origin. So if you take these displacement boundary conditions, so it is given to you that u of x at origin is 0. This implies you put x equal to 0 here in u of x. So what you will get? X equal to 0, y equal to 0, all these terms will go to 0 and you get f of 0. So f of 0 should also be equal to 0. So this implies f of 0 should also be equal to 0. Similarly, you have u of y at origin equal to 0. This implies your g of 0 should also be equal to 0. You can put in that equation here. So if you put here, so x and y are 0 and g of 0 should also be equal to 0. Only then this condition will be satisfied. And then you have finally rotation gamma xy at origin, so that is 0. So gamma xy is given by half of del x by del y minus del uy by del x. So that at origin, if you calculate, so that is 0. So del ux by del y, if you calculate, so that is nothing but f prime y, and del uy by del x, that is nothing but g prime x. So both at origin are 0, right? So it means your f prime 0, because x is 0, y is 0, should be equal to g prime 0, right? So these are three conditions. So your f of 0 is 0 means what? So your f of 0 means your c2, f of 0 will be c2, so this implies your c2 should be equal to 0. And g of 0 means what? You apply g of 0, so if you apply g of 0 it means what? 10 minus f prime 0. Obviously this term will go to 0. It means c2, this is also giving you c2 equal to 0 actually. So okay, we can take c3 actually, this is not c2. It can be different from what you are getting in f. So yeah, so here integration constant is c3, So because this can be different from these two constants, so here you will get C3 equal to 0. And from this condition, f prime equal to 0 is equal to g prime equal to 0, what will you get? So let's find out what is f prime 0 first, and then we'll find g prime 0. So I'm just writing this equation again here. Okay, so we have this equation f prime y is equal to 10 minus g prime x. So you put x equal to 0, y equal to 0 here. So f prime 0 should be equal to 10 minus g prime 0. So if you solve this, because f prime 0 is equal to g prime 0, so here you will get f prime 0 is equal to g prime 0 is equal to 5. Right? So you have now all the terms. You have the value of C2, you have the value of C3, and you have the value of C1 also, because C1 is nothing but f prime y or f prime 0. If you put y prime 0 also, you will get C1. Y is equal to 0 also, then you will get C1. So yeah, you have the value of C1 also. C1 is 5. From here you can say C1 is 5. So now you have all the values. So using these three conditions, we have found out the value of this three constants C1, C2, C3. So now finally we have the expressions. So that's why your f of y now of y will be what? So this is C1 y plus C2. C1 is 5, y is y, and C2 is 0. And now you have g of y. So g of y is 10 minus f prime y, which is C1, which is 5, times x plus C3, which is 0. So you get 5x. Right? Okay. So you can put in the expression of ux and uy. So you will get, therefore, the displacement components are ux is equal to, just wait a minute. So ux is equal to 5x plus x3 by 3 plus y square x plus x5 by 5 plus xy4 is 5y, and uy is equal to 6y. I'm just putting the value of f of y in u of x. Y cube plus x4y plus y5 by 5 is 5x. So these are the final displacements that you have, and you can find out the, so you can solve for second part as well. But let me just uh, tell you what we have done finally. So here we had the relationship between f prime y and g prime x, which we got from by equating gamma xy. Okay, but we wanted to find out the exact expression for f of y and g of x. Okay, so we had three conditions. So from here you can express f prime y is equal to 10 minus g prime x. This whole thing can be a function of x. Okay, because but this is not a function of y for sure. So if you integrate this, you will get 10 minus g prime x dy. So this can be written as 10 minus, so c1 is nothing but 10 minus g prime x y plus c2. C1 is 10 minus prime x. Okay. So but I have written 10 minus g prime x equal to c1. Similarly, g of x has also been written in terms of f prime y. So here you have these two integration constants, right? And you have the value of, you should know the value of this f prime and g prime, f prime y and g prime x also, in order to get f of y and g of y. Okay, so basically you have four unknowns, you can say. You have four equations also. First equation is this, that is relating f prime and g prime x, and then three equations are this. So from these four equations you can find this c2, c3, and then this f prime y, and here also, here this is, since this is 10 minus g prime x, this is g prime x. So you can find all these four things. That's what we have done. In the part B, what you need to do, so you need to find out for the given of state of strain. For the state of strain given in previous problem, write down the volumetric and deviatoric parts. Also determine the volumetric strain. Previous problem is this problem only, this part A it is referring to. So you have to find volumetric and deviatoric parts, and you have to determine the volumetric strain. So now you have the expressions, you can easily find out. So volumetric strain. Firstly, let's find out volumetric strain tensor. So that will be given by 1 by 3 J1 first invariant in I. And J1 is nothing but this is given by epsilon xx summation of trace of, and this will be the trace of strain tensor. So epsilon xx you can easily find out, because this will be del u x by del x, del u y by del y, and this is obviously 0. So if you do that, so you just have to differentiate del u x by del x, so you will get 5 plus x square. It's given to you in the question only, epsilon xx and epsilon y. You just add it and you will get. So this is epsilon xx. Obviously I have forgotten it. So yeah, so this is x square plus y square plus x4 plus y4, and this is 6 plus 3x square plus 3y square plus x4 plus y4, and last one is 0. So finally you are getting j1 is equal to 6 plus 5 plus 11, x square plus 3x square is 4x square plus y square is also 4y square plus 2x4 plus 2y4. So you need to find out volumetric part of strain, strain tensor. That is 1 by 3 j1 times I. j1 is 11 plus 4x square plus 4y square plus 2x4 plus 2y4 times I. And then you have to find volumetric strain. And obviously you can find out deviatoric strain tensor. So you need to do that epsilon minus the whole strain minus this volumetric part. That's this you can just evaluate it, because you have this strain tensor. Now you just write using these components, you can write strain tensor, and if you subtract this volumetric part from that strain tensor, you will get the deviatoric part. This is your deviatoric strain tensor. Now you need to find out volumetric strain also. So that is, that is given by trace of strain tensor. So that we have already found out. That is given only. So 11 plus 4x square plus 4y square plus 2x4 plus 2y. This is the final expression. Okay, so we will stop here for today. If you have any doubts related to this session, you can ask me in the next class. Thank you for attention of all of you.